In this episode, we focus on data pipelines, because in AI systems the pipeline is often where risk quietly enters long before anyone notices a problem. A data pipeline is the path data takes from where it originates to where it is used, including collection, cleaning, transformation, storage, movement, and eventual use in training or inference. Beginners sometimes picture data as a static file that sits in one place, but pipelines are more like rivers that keep flowing, branching, and changing shape. When the pipeline is not controlled, data can be copied to unsafe locations, modified without trace, or accessed by people and services that should never have seen it. A secure pipeline is not about making data hard to use. It is about making data use predictable, auditable, and safe. The three focus areas in this title are lineage, access control, and secure storage, and together they create a foundation for trustworthy AI. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Data lineage is the first pillar, and it simply means you can trace where data came from, how it changed, and where it went. Think of lineage like a chain of custody in a serious investigation, where you must be able to show who handled an item, when they handled it, and what happened to it along the way. In AI, lineage matters because model behavior is shaped by data, and if you cannot explain your data, you cannot defend your model decisions. Lineage also matters because data can be wrong, biased, or contaminated, and you need to be able to identify which model versions were affected by which data. Beginners often assume that once data is in the system, it is trustworthy, but data can be corrupted by simple mistakes, such as incorrect labels, missing records, or unintended mixing of datasets. Lineage is how you detect and correct those problems and how you prove, later, that you used data responsibly. Lineage has a security dimension as well, because attackers can target data pipelines to influence outcomes. If an attacker can inject malicious records into a training dataset, they may be able to manipulate model behavior or create hidden backdoors that activate under certain inputs. If an attacker can modify a reference dataset used during inference, they may be able to cause wrong answers that look legitimate. Lineage helps you identify when and where data changed, and that makes tampering easier to detect. It also supports response because if you find a poisoned dataset, you can trace which models were trained on it and decide what must be retrained or retired. Beginners should see lineage as both a quality control tool and a security control because it protects integrity and supports accountability. Without lineage, you are often forced to guess, and guessing is the enemy of reliable risk management. Lineage is built by capturing metadata at key points in the pipeline. Metadata is information about the data, such as where it originated, when it was collected, what transformations were applied, and what approvals governed its use. You do not need to imagine specific tools to understand the concept. The important idea is that pipelines should record their own history. If data is cleaned, the pipeline should capture what rules were used and what records were removed or altered. If data is labeled, the pipeline should capture who labeled it, what labeling standards were used, and what quality checks were performed. If data is combined from multiple sources, the pipeline should record which sources and how they were joined. Beginners sometimes fear metadata will slow everything down, but the reality is that good metadata prevents future confusion and rework because it creates a reliable map of what happened. Access control is the second pillar, and it addresses a simple truth. Not everyone who can benefit from AI should be able to access all the data that powers it. Access control means only approved identities can view, modify, or move data, and those permissions are limited to what is needed. In data pipelines, access control applies to multiple points, including raw data ingestion, intermediate processing stages, storage locations, and any datasets used for training or retrieval. Beginners sometimes assume that data access is a single gate, but pipelines often involve many temporary locations where data can be exposed. If access control is strong only at the final storage location but weak in intermediate steps, data can leak through the cracks. Access control should therefore be applied consistently across the pipeline, not just at the end, because the pipeline is a system of many hands and many containers. Least privilege is especially important in data pipelines because broad access creates both accidental and intentional risk. If a service account used for a small transformation step can access all datasets, that account becomes a powerful target. If a developer has broad access to production data to troubleshoot a pipeline, that access can lead to accidental exposure or misuse. Strong access control assigns roles such that pipeline components have only the permissions required for their function, and humans access data through controlled pathways with logging and approvals. Separation of duties also matters, because the person who can change pipeline logic should not automatically be the same person who can approve the use of sensitive data. Beginners should remember that access control is not about distrust. It is about minimizing risk by limiting who can touch high-value assets. When access is limited, the blast radius of any mistake or compromise is smaller. Secure storage is the third pillar, and it deals with where data lives and how it is protected while at rest. In AI pipelines, data can exist in multiple storage forms, including raw ingestion storage, clean datasets, feature stores, training datasets, and logs. Secure storage means these locations are protected so unauthorized users cannot read or alter data, and it also means the organization can manage retention so data is not kept longer than needed. Encryption is often part of secure storage, but secure storage is broader than encryption alone. It includes access controls on storage, monitoring of access, protection against unauthorized changes, and backups that prevent data loss. Beginners sometimes focus only on confidentiality, but storage must also protect integrity, because altered data can be just as harmful as leaked data. Secure storage is the stable foundation of the pipeline, because insecure storage turns every upstream control into a fragile promise. Secure storage also includes thinking about copies, because pipelines create copies naturally. Data is cached for performance, copied for processing, and stored in logs for troubleshooting, and each copy can become a leakage point. A common beginner misunderstanding is believing that because the primary database is secure, the data is secure everywhere. In reality, the most dangerous data store is often the one nobody remembers exists, like a temporary staging area or an old backup that is accessible to too many people. Controlling the pipeline means identifying where copies are created and ensuring they follow the same protection rules as the original data. This includes retention decisions, because data kept indefinitely becomes a larger and larger liability. Secure storage practices therefore require both a technical posture and an organizational discipline about what is stored, why it is stored, and when it is deleted. These three pillars, lineage, access control, and secure storage, reinforce each other, and the strongest pipelines treat them as one system. Lineage without access control tells you what happened, but it does not stop unauthorized access from happening. Access control without lineage can stop some misuse, but it can leave you blind to subtle changes and contamination. Secure storage without the other two can protect a database, while leaving the pipeline steps exposed and untracked. Together, they create a pipeline you can trust because it is both protected and explainable. In AI security management, explainability is not only about model outputs, it is also about data provenance and handling. When you can show where the data came from, who accessed it, and how it was protected, you can defend the system to leaders, auditors, and users. Beginners should see this as building trust through discipline rather than through claims. Another important aspect is that pipelines are not only for training data. Pipelines also exist for inference time data, such as user prompts, retrieved documents, and inference logs. These data flows can be sensitive and can be used for monitoring, improvement, and incident response. If inference logs are collected without access control, they can leak sensitive user information. If prompts are stored without clear retention, they can create a large sensitive dataset that becomes a target. Lineage for inference data helps you understand what information influenced an output and whether that information should have been included. This matters for both security and fairness, because an output can be harmful if it is based on inappropriate or outdated context. Controlling these pipelines is part of treating AI systems as responsible systems rather than as black boxes that generate text. Data pipeline control also supports model validation and incident response in practical ways. Validation depends on knowing what data was used and whether it was appropriate, because poor data hygiene can masquerade as model weakness. Incident response depends on knowing what changed in the pipeline, because many incidents trace back to a data change rather than a code change. If a model begins producing unsafe outputs, you need to know whether the training data changed, whether a retrieval source changed, or whether logs show unusual access patterns. Lineage provides the timeline, access control limits who could have caused the change, and secure storage protects the evidence, so it is reliable. Beginners should notice how these controls create a complete story where you can investigate with facts rather than speculation. That investigative ability is part of operational trust, because you cannot manage risk without understanding causes. As systems grow, controlling data pipelines becomes more challenging because complexity increases. More sources, more transformations, and more users increase the chance of mistakes and increase the opportunities for attackers. This is why standardization matters, because consistent patterns for lineage capture, access roles, and storage protection reduce the number of unique exceptions. It also helps to treat pipeline changes as high-risk changes, because small changes can have big consequences. For example, adding a new data source might introduce sensitive information unexpectedly, or changing a transformation rule might remove a key privacy filter. A mature approach reviews and validates pipeline changes before they affect training or production behavior. Beginners should understand that pipelines are critical infrastructure for AI, and critical infrastructure deserves careful change control, not casual tweaking. To close, controlling data pipelines with lineage, access control, and secure storage is one of the most effective ways to reduce AI risk because it protects the system at its foundation. Lineage ensures you can trace data from origin through transformation to use, supporting accountability, quality, and tamper detection. Access control ensures only approved identities can view, change, or move data, limiting both misuse and accidents through least privilege and separation of duties. Secure storage protects data at rest across all pipeline stages and copies, including retention discipline so old data does not become future exposure. When these three are applied consistently, AI systems become more trustworthy because you can prove what data was used, who touched it, and how it was protected. Task 14 is ultimately about building that trust, because safe AI depends on secure, explainable data handling long before any model produces its first output.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.